Hello everyone, this is Joey. I'm a PhD candidate from Columbia University DB/MM Lab, advised by Professor Shifu Chang. On behalf of the team, it's a great honor for me to share our paper, DiGeo, the Discriminative Geometry-Aware Learning for Generalized Few-Shot Detection. In this project, we specifically focus on the task of generalized few-shot detection, where the detection precision for classes with either sufficient number of training data or limited number of training data should be considered. In particular, we analyze the popular transfer learning framework and point out the downsampling step in transfer learning is important for efficient few-shot adaptation, but it's also the root reason for severe base forgetting. As such, we propose to solve this embarrassing trade-off from the perspective of feature geometry and design a new framework. For few-shot learning, a common pipeline is to first pre-train the model on base site with sufficient number of training data. Then we do adaptation on the few-shot classes, which are called novel. However, different from average classification, where there is only one object instance centered at the image. For the object detection, there could be multiple instances in one image, and the instance can be from both the base and novel classes. Thus, it is important to ensure the performance for both base and novel classes. And even for the cross dataset adaptation, when there are class-level overlapping, for example, the class of airplane exists in both MS-COCO for pre-training and satellite images in adaptation. It is good to keep and even utilize the pre-trained knowledge. For the few-shot detection, there are typically two representative approaches. The first one is called meta-learning framework, which is essentially performing pairwise comparison. At the inference time, given a test data, it will be compared with each of the labeled training data. However, since the meta-learning framework always does instance-level comparison, it cannot learn a discriminative classifier for base classes, where each weight vector in the classifier can serve as the global center for all instances in this class. Then, the detection precision for base classes is far below than the precision obtained in fully supervised manner. In contrast, for the transfer learning approaches, it first learns a good base detection model at the pre-trained stage. However, during the few-shot adaptation, we need to first downsample the base train set to build a balanced dataset among the union of base and novel classes. As the model does not effectively utilize the diversity of base train set, it will suffer from severe base forgetting. Then, a natural question being raised is whether or even why do we need to do the downsampling? We provide analysis from the perspective of feature geometry, and we first consider the interclass separation and compare the classifier weights learned under different setups. As shown here, in each of the three plots, we calculate the pairwise cosine similarity between the class centers, and we use deeper color to indicate higher similarity. From the first plot, we can see that if we use the full set, which consists of all training data for base and null classes, due to the severe imbalance between the base train set and novel train set, the classifier weights for novel classes will not be properly learned. Instead, they are close to each other and thus cannot be used for classification. In contrast, when we use the balanced dataset for adaptation, as shown in the middle plot, we can see that all of the classifier weight vectors can be poorly separated from each other. Lastly, when we only use the train set of novel classes for adaptation, it is intuitive to say that the separation of classifier weights of base classes is hurt. However, it is still interesting to say that the separation of novel class centers is not as good as the one obtained through fine-tuning on a balanced dataset. And we think the main reason is that the training data of novel classes is extremely limited, and adding a few more instances even from other classes can still benefit the interclass separation of novel classes during the optimization. Then, from the perspective of interclass compactness, we compare the similarity between the instance features and class centers and summarize them over the classes. And similarly, Since we have a limited number of training data for future classes, we can say that the embeddings of those training data are still distant from the corresponding centers. With the analysis above, we propose a new end-to-end framework for the generalized few-shot abduction and considers both inter-class separation and intra-class compactness. Since it is hard to learn a good classifier on imbalanced dataset, we then choose to predefine the classifier whose weight vectors are maximally and equally separated from each other. And this is called simplex equiangular tight frame. Then for the simple ETF, each weight vector is class center and fixed during training. In this way, we are using the fixed classifier weights to guide the learning of instance embedding. For the intra-class compactness, we choose to modify the vanilla cross-interface loss by adding class-specific margins and push the features close to the corresponding class centers. In this way, we directly train our approach on the entire training dataset to both utilize diverse training data of base classes and also achieve effective few-shot adaptation. By comparing the similarity between the instance features and class centers, the features of all classes are better clustered. Through experimental study, we also achieve consistent proper scan on generalized few-shot abduction and long-tail abduction. We hope our work can provide more insight towards the few-shot adaptation and training on imbalanced dataset. We have also released our code, and please feel free to drop us email if you have any other questions.